So in this chapter, we've been going over properties and behaviors of gases, including the gas laws. And one of the main properties and variables of gases that we have to pay extra attention to is pressure. And so we haven't talked too much about pressure in this class thus far. And so our first question deals with the conversion of different pressure units. And so the two main pressure units that we are going to use in this class is atmospheres and millimeters of mercury. And so we'll look at question 7 and we'll concentrate on part B, because those are that involves the two units that we are going to use in this class. And so our conversion from for atmospheres and millimeters of mercury is 1 atmosphere is equal to 760 millimeters of mercury. So what we want to do is, if we know we have 2.00 atmospheres, we need to set up a conversion factor to solve for the millimeters of mercury. And so we know that atmospheres must be as the denominator, because we want atmospheres to cancel out. And we know we want millimeters of mercury to be as our numerator, because that's what we want to be left over. And so 1 atmosphere is equal to 760 millimeters of mercury. And so we have our atmospheres cancel out, and we're left with millimeters of mercury. And so when we solve for that, we get 1,520 millimeters of mercury. And that will be our conversion from atmospheres to millimeters of mercury. The next question that we'll look at is when we have initial conditions of a 10-liter balloon of helium gas that has a pressure of 655 millimeters of mercury. And then we need to solve for the new pressure in millimeters of mercury given these new volumes. And so we'll solve this in two different ways, all right, but we'll use the same equation. So they're just depending on what you would prefer to do. So we'll use the equation P1V1 equals P2V2, and we know to use that because we have liters and millimeters of mercury. All right, liters is a measurement of volume, and millimeters of mercury is a measurement of pressure. And so those are the only two variables that were given in this problem. And so we have a pressure of initial pressure of 655 millimeters of mercury, and we have an initial volume of 10.0 liters. We're going to do question part B to start off with. And so we'll have to solve for the new pressure given the new volume of 2.50 liters. And so what we'll do is we'll multiply 655 times 10, and we get 6,550 millimeters of mercury liters is equal to P2 times 2.50 liters. Divide both sides by 2.50 liters, and we will get 2,620 millimeters of mercury as our new pressure. And so that was part B, and the next one we'll look at is part C. And so here, what we can see is that we have units of milliliters here and liters here. So we want to do a conversion. And so you can set up the conversion factor, or even more easily, we know we can use the King Henry died drinking chocolate milk method of moving the decimal place over, and we know we need to move the decimal place over 3 places to the left. So 1, 2, 3. And that will be 1 0.500 liters. So we want to do that to start off with. We'll do another method in solving for the final pressure. And so what we'll do is we'll solve for the equation with just the variables. So we'll solve for P2 in terms of just the variables. So P1 V1 is equal to P2 V2. And so we want to get the final pressure P2 by itself. We want to divide both sides by V2. And we get P1 V1 divided by V2 is equal to P2. Now we can just put in our numbers. We still have the same initial conditions of 655 millimeters of mercury and 10.0 liters. And now our volume, our new volume, V2, is 1.500 liters. And so we'll solve this out. And 655 times 10 divided by 1.5 is equal to 4,367 millimeters of mercury. And so we can just go back and make sure that this makes sense. And so pressure and volume should have an inverse relationship. So if pressure goes up, then volume should go down. And so, and vice versa. And so in part C, what we see here is we're going from 10 liters to 1.5 liters. So pressure of the volume is decreasing. So that means that we should have an increase in pressure. You're basically just putting all this same amount of stuff in a smaller place, in a smaller container. And so there's going to be a lot more pressure. And the same thing goes with part B. You're putting all of that gas that was in 10 liters, a container or 10 liter balloon, and you're putting it in a smaller place. You're putting it in a smaller volume, and so that pressure is just going to build up. You're going to have a higher pressure, and that's what we see in both cases. The next question we'll look at is 7.25. And so here we have a sample of neon that has an initial volume of 2.5 liters at 15 degrees Celsius, and we need to figure out the new temperature given these changes in volume. And we're told that pressure and the number of moles of gas do not change. So we'll just pick out two of them. We'll just pick out A and B. And so one thing that you want to pay special attention to is the temperature. And so whenever we have a gas problem, or really most chemistry problems, if we have a temperature in terms of degrees Celsius, we want to do a conversion of degrees Celsius to Kelvin. And so that's what we'll do initially. And so 15 degrees Celsius is equal to 15 degrees C plus 273 Kelvin, which we get 288 Kelvin. Okay, so we'll just add 273, and that's how you get Kelvin. And then we'll do A in both formats, and so we're relating volume and temperature. And so we have one equation that relates volume and temperature. And so that equation is V1 over T1 equals V2 over T2. All right, and so here we will we have an initial volume of 2.50 liters, an initial temperature of 288 Kelvin. We have a final volume in A of 5.00 liters, and we're trying to solve for T2. So we cross multiply, and we get 2.50 liters times T2 is equal to 288 Kelvin times 5.00 liters. So we'll solve for that, and we have 2.50 liters times T2 is equal to 1440 Kelvin liters. And now we want to divide both sides by 2.50 liters. And we get T2 equal to 576 Kelvin. So we can go back and, like we did with the last question, we can try to see if this answer makes sense. So in V1 over T1 equals V2 over T2, they have a direct relationship. So if the volume goes up, the temperature goes up. If the volume goes down, the temperature should go down. And so here in A, we have an initial volume of 2.5, and it's going up to 5. And so we should see an increase in volume, so we should see an increase in temperature. And so here we have an initial temperature of 288 Kelvin, and we have a final temperature of 576 Kelvin. So indeed, it does go up. And I noticed that it asked for the degrees Celsius, and so we need to just go back and subtract 273, and we get 303 degrees Celsius. All right, and so you can do it. You can solve for questions like this in that way, or you can go back and use the variable, solve for the variable with the in terms of just the letters. And so we're trying to find T2. So we want to we'll just write out V1 over T1 equals V2 over T2. We'll cross multiply, and we get V1 times T2 equals V2 times T1. We're trying to solve for the new temperature, so we divide both sides by V1. And so T2 is equal to V2 over times T1 over V1. All right, that's just another way to solve for it. And so here in B, we notice that we have liters and we got milliliters. So again, we need to do our conversion. So our decimals after the 0, 1, 2, 3. All right, want to move over 3 spots. So we get 1.25 liters. And so our V2 is 1.25 liters. Our T1 is still the 288 Kelvin. And our V1 is the 2.50 liters. And so just do this out. 1.25 times 288 divided by 2.5. And we get an answer of 144 Kelvin. And so when we put that, it asks for degrees Celsius. So we subtract 273. And we get negative 129 degrees C. And so here we see that volume goes down. And so then temperature should go down. And indeed it does. It goes from 15 degrees C to negative 129 degrees C. Okay. The next question we'll look at is a very similar question. We'll just do one of these. And this is just applying the same equation, but instead of solving for temperature, we solve for the new volume. So we're still going to use the V1 over T1 equals V2 over T2. And so we'll just do a question A. And so it says we have a volume of 2,500 milliliters at 75 degrees C. What's the new volume given the new temperature, which is in A, 55 degrees C? And so our volume is 2,500 milliliters. It wants the final volume in milliliters as well, so we don't need to change anything. Our T1, well, we have the initial temperature of 75 degrees C, but we need to convert that to Kelvin. So 75 degrees C plus 273 Kelvin gives us 348. And then we'll put that there. Our V2 is what we're trying to solve for, and T2 is 55 degrees C. Need to add 273, and so we get 328 Kelvin. So we'll put 328 Kelvin there. And so here we just cross multiply and divide. So 2500 times 328. We get a large number of 820,000 milliliters Kelvin equal to V2 times 348 Kelvin. Divide both sides by 348 Kelvin. And we get a new volume of 2,356 milliliters. Doesn't have the correct number of significant figures, but that's that, you know, for all intents and purposes, it's fine. And so there you go. And so here we saw that the temperature decreased. So we should have saw a decrease in volume, in which we do. 2,500 is greater than 2,356. So volume did indeed decrease. So here we have a question. It wants us to relate, so for the following, calculate the final temperature of the gas in degrees Celsius when the initial pressure is changed with volume and the number of moles constant. So here we're relating temperature and pressure. And so pressure and temperature, we have an equation of P1 over T1 equals P2 over T2. And so we'll look at, we'll just do letter A. And so it says that we have Z at 25 degrees C. So right there we can just stop and see degrees C. We need to convert that to Kelvin. All right, so 25 degrees C plus 273 is equal to 298 Kelvin. And then we have initial volume, initial pressure of 745 millimeters of mercury, and then we have final pressure of 625 millimeters of mercury. So we'll just go ahead and put these numbers in. So pressure 1 is 745 millimeters mercury. T1, 298 Kelvin. Then we have P2 is 625 millimeters of mercury. And then we have T2. So cross multiply. All right, and so we get 745 millimeters of mercury times T2, all right, cross multiply, is equal to 186,250 millimeters mercury per times Kelvin. Then lastly, divide both sides by 745 millimeters of mercury. And so we will get T2 equal to 250 Kelvin. And it wants us to have that final temperature in Celsius to make more work for us. So subtract 273 and we get negative 23 degrees Celsius. And so we have pressure and temperature have an inverse relationship. So if pressure is decreased, as in this case, then we should see an increase in temperature, which we do not. Oh, that was my mistake. They have a direct relationship, and so we actually do have the correct observation in that we saw pressure and temperature are directly related, so we saw a decrease in pressure, and so we should have seen a decrease in temperature, in which we do. We went from 25 degrees Celsius to a negative 23 degrees Celsius, and so we are safe with our answer. Conceptually as well as quantitatively. Now we are given a question. It says we have a sample of helium gas with a volume of 6.50 liters, pressure of 845 millimeters of mercury, and a temperature of 25 degrees C. What's the final pressure in atmospheres when we have these different volumes and temperatures? So here we have three variables to work with. So if we have three variables, which are pressure, temperature, and volume, we have to use the combined gas law. P1 times V1 over T1 is equal to P2 times V2 over T2. So we'll do question A. And just to keep all of these variables and keep that track of them, we'll just write everything out on the side. So 6.50 liters is our initial volume, V1. We have a pressure of 845 millimeters of mercury. That's P1. But instead of just leaving it like that, it says it's going to want our final pressure in atmospheres. So let's just go ahead and convert that to atmospheres now. So we'll set up a conversion factor. We want millimeters of mercury to cancel. We want atmospheres to remain. So 1 atmosphere is equal to 760 millimeters of mercury. And so we divide 845 divided by 760, and we will get 1.11 atmospheres. Cool with that. And then T1 is 25 degrees C. We need to convert that to Kelvin. Plus 273 gives us 298. Then we have V2 is equal to, we have liters here, we have milliliters here, we need to convert 1850 liters, milliliters, convert that to milliliters, convert that to liters, I should say. 1, 2, 3 equals 1.85 liters. Then we have a T2 equal to 325 Kelvin. So, after all of this, now we can get to the problem and using the combined gas law, if it wasn't enough already. So, we will just go ahead and solve for P2 in terms of our variables. So we're going to cross multiply first. P1 V1 times T1 is T2, I should say, is equal to P2 V2 times T1. And we want to solve for the final pressure. So we'll divide both sides by V2 and T1. And so we get P1 V1 T2 over V2 T1 equal to P2. Now, lots of letters with numbers. Alright, now we just plug in our numbers. So, P1 was equal to 1.11 atmospheres. Time to give some room. V1 was equal to 6.50 liters. T2 was equal to 325 Kelvin. So much stuff on this piece of paper is getting squished together. V2 is 1.85 liters. T1 is equal to 298 Kelvin. And now what's left is just plugging this back into our calculator and getting our value. And we get a number of 4.25 atmospheres, which doesn't seem unreasonable. Alright. So, that was a combined gas law equation and problem. Moving on. Look at question 53. Here we have an oxygen gas container with a volume of 20.0 liters. It's asking how many grams of oxygen are in the container if the gas has a pressure of 845 millimeters of mercury at 22 degrees Celsius. So here we're going to have to use the ideal gas law. Pivnert. PV equals nRT. That R is the universal gas constant. I have always just used the 0.0821 liters atmospheres per mole Kelvin. And that's the units I like to work with. That's the one I always use. Okay. If you want to use the other R, you're more than welcome to use the other R in terms of millimeters of mercury instead of atmospheres. So, we got some conversions to do. We have our volume as 20.0 liters. So we're good with that. Right? We want liters. Here we have atmospheres. Here we have millimeters of mercury. So we have a conversion to do. P is equal to 845 millimeters of mercury. We want millimeters of mercury to cancel out and be left over with atmospheres. 1 atmosphere is equal to 760 millimeters of mercury. So, 845 divided by 760, and we get a nice 1.11 atmospheres. N is essentially what we have to solve for. That will give us number of moles, and then from there we can solve for the mass. We'll just break it up in that way. You can rearrange the equation so that you can get mass, but we'll just stick with this and just do it in 2 steps. And then T is equal to 22 degrees C. We see here we got Kelvin, so we need to convert this to Kelvin, add 273, and we get 295 Kelvin. So now we can just plug it in and solve. Plug and chug. We get 1.11 atmospheres. We get a volume of 20.0 liters equal to N times 0.0821 liters atmospheres per mole Kelvin times temperature 295 Kelvin. So 1.11 times 20 is 22.2 atmospheres liters equal to N times 0.0821 times 295. We get 24 point, we'll just use 3 sig figs, 2, and liter, atmosphere, mole, Kelvin. Oh, Kelvin cancels out. Alright, now divide 22.2 divided by 24.2. And we get 0.917 moles is equal to N. Liters and atmospheres cancel out. And, of course, we're not done. Now we need to convert the moles to mass. So, oxygen gas is O2. And that has a molar mass of 32 grams per mole. And so we take 0.917 moles times, we want grams on top, moles on bottom. We have 32 grams per 1 mole. So we take our 0.917 times it by 32 and we get a nice 29.4 grams of O2. And that gives us what we want. All right, there we go. The next one we'll look at, a little different format than our usual. It is a, let's see if I can get this light on. A little bit better focus there. So here, it's asking for what is the molar mass of an unknown gas in a 1.5 liter container, and you can read the rest of the question. All right, and so again, here we're going to start off with PV equals nRT, but we're trying to figure out the molar mass. So this is where I was saying you can put mass into this equation. We know that molecular weight is equal to mass over moles, grams over moles, which is mass over moles. So we can rearrange that. All right, N is moles. So we can convert, cross multiply and divide, and we'll get moles is equal to M over MW. Mass over molecular weight. And so that's what we're going to put here. PV is equal to mass over molecular weight, RT. This question wants us to solve for the molar mass. And so you could do a couple things. You could rearrange the equation so that molar mass was all by itself, or you can put your numbers in and solve as we've been doing. And so that's what we'll just continue to do. So R is equal to 0.0821 liter atmosphere mole Kelvin. So we're going to make sure all of those units are intact. P is in atmospheres, volume is in liters, and of course temperatures in degrees Celsius. So 19 degrees C plus 273 is equal to 292 Kelvin. So pressure is equal to 0.0750 atmospheres. Volume is equal to 1.50 liters. Our mass is equal to 0.488 grams. Our R, 0.0821 atmosphere, liter, mole, Kelvin. And temperature is 292 Kelvin. So, put this in our calculator. We get 0.112 1125 atmosphere liter. Oh, forgot the MW is equal to 0.488 times 0.0821 times 292, and we get 11.7 atmosphere liter gram mole, and our Kelvin cancel out, and this is divided by MW. So cross multiply and divide, and essentially becomes 11.7 atmosphere liter gram per mole divided by 0.1125 liter atmosphere. So our liter atmospheres cancel out. And so we get 11.7 divided by 0.1125, and we get 104 grams per mole is equal to molecular weight. If you could not see where I got this, I'll just do it out real quick. And so it was 0.1125 equal to 11.7 divided by MW. 1.1125 times MW equal to 11.7. And I get MW is equal to 11.7 over 0.1125. Okay, so I just skipped a couple steps there. Alrighty, that's how we solve for that. That was a nice long one. You always gotta like those questions that take a full sheet of paper. Alright. Focus this in. Alright, there we go. Cooperating now. Alright, try to finish this before my battery dies. So we have a gas mixture containing oxygen, nitrogen, helium, exerts a total pressure of 925. So P total equal to 925 torr. If the partial pressure of oxygen are 425 and helium 75, what's the partial pressure of nitrogen? And so the P total, in this case, we have three gases. We have the pressure of oxygen, we have the pressure of nitrogen, and we have the pressure of helium. Alright, so the total pressure is equal to the sum of the partial pressures. And so we have three partial pressures, three different gases here. The pressure of oxygen is equal to 425, and the pressure of helium is equal to 75 on torr. And so the total pressure is 925 torr. Our pressure of oxygen is 425 torr. Pressure of nitrogen is our unknown, and pressure of helium is 75 torr. So we get 925 torr is equal to 425 plus 75 is 500 torr, plus the pressure of nitrogen. So we subtract 500 on both sides and we get 425 torr is equal to the partial pressure of nitrogen. And so double check, we get 425 plus 425 plus 75, and we get a total of 925, and indeed we are good. And so that's how you solve for partial pressure using Dalton's law. And so that is the conclusion of this installment of work through examples for Chapter 7, Gas Laws.